All right, so we're going to finish this semester talking about physical optics. But before we do that, or to set that up, what we're going to do is we're actually going to step back to talking about interference, which is really sort of what's going to make our physical optics mean something. So if you remember from 298 when you talked about interference there, you talked about the fact that what interference is it's paying attention to the way that waves add up. And waves, when we add waves together, we care about their phase. So here in a very basic situation, I have two identical waves, wave 1 in blue, wave 2 in red. And again, right now, the red wave is sitting right on top of the blue one. So they are perfectly lined up. Every place where the red one's a peak, the blue one's a peak. Every place where the red one's a trough, the blue one's a trough. Every place where there is zero amplitude for the wave, it's the same for both the red and blue. So here are two identical waves that are perfectly in phase with each other. And so what we can do is we can basically start sliding one of these waves relative to the other. So in this case, we'll let the blue one stay where it is, and we'll start to move the red one to the left. And so what you'll notice is that the resultant wave, that's the purple one, and again, you get the resultant wave by basically just saying, well, add up however much the blue wave is plus however much the red wave is. You get what the resultant wave starts doing is when we started, right? So right here, notice that since I have two identical waves, the resultant wave happens to be twice the amplitude of my two individual waves. So they were both, let's say the scale is in meters, so I had two waves that had a 1 meter amplitude, and the resultant wave is 2 meters in amplitude. Well, as I start sliding one of them relative to the other, notice what happens to the amplitude of the resultant wave. It's decreasing, and eventually it ends up in a situation where now my waves are mostly canceling each other out. So now what I've got is in a situation like this, right? So pick any point you want. Here we'll happen to pick, let's say we happen to pick, oh, I don't know, right here. Right? So here's a situation where you've got the blue wave is half a meter above, but the red wave is something, like 0.85 meters below. And so when you add those together, the resultant still ends up being below. And so now the maximum, the peak of my wave is much smaller than the two individual waves. And again, as I keep sliding them, it just gets smaller and smaller until I reach a situation where now where the red wave is at a peak, a positive maximum, the blue wave is at a trough, a negative maximum. And so when I take basically +1 and add -1, I get 0. And pick any point along the wave, and what you've got is any point, add together the blue wave and the red wave, it's always going to give you 0. So here, my waves are what's known as perfectly out of phase. They're canceling out. So again, what we care about when we're dealing with interference is we care about the relative phase between our two waves. Now again, if I keep sliding the red wave, well, you notice that what's happened is, so this peak that was initially lined up with this blue one, well, now as I keep sliding it, it starts to line up with the next peak over. And so as it starts to line up, the resultant wave gets bigger and bigger again, until again I end up in a situation where they're completely lined up, they're back in phase, and so I end up with a resultant wave that's twice as tall as each of the individual waves. So basically what this comes down to is what I'm going to care about is the phase difference. And the phase difference when we're dealing with waves we usually denote by delta phi. So this is the phase difference. It tells me what's the relative phase between my two waves, and I'm going to care about that when I go to add them up. Now, the easiest way to get a phase difference, so there's sort of two ways that are fairly straightforward to go about this. One is, well, I can have two sources that are not in phase. So here if I got source A and here I've got source B, and if they're not in phase, then I'm probably going to end up with a phase difference between my two waves. But the one that we're going to focus on is actually the second one. So I'm going to have two sources that are in phase, but their signals are going to travel different distances. So if you look at this picture here, again, I've got source A and source B, and these two waves are in phase. Notice that basically they're starting at 0 and starting with a positive peak. So starting at 0, starting with a positive peak. So they're perfectly in phase, but what you notice is, because we have a 3, 4, 5 triangle here, right, my red wave only travels 4 meters, my blue wave travels 5. So that additional distance that the blue wave travels now matters. And so depending on how much longer I make one wave travel than the other and what their wavelength is, I can induce a phase difference. So here, again, you'll notice that, so 4 meters, that's how long the red wave travels. That basically gets me to this point. But I've got an additional distance here that's called the path difference. So we talked about the phase difference, that's delta phi. The path difference is delta lambda. And so what I'm going to care about is I'm going to care about when I have two sources that are traveling, that are sending out waves in phase that are traveling different distances. I'm going to care about that path difference because I can relate the path difference to the phase difference. So we said in this case, for our example, this path difference is just going to be 4 meters minus, or 5 meters minus 4 meters, which is 1 meter. So the blue wave coming from source A traveled 1 meter more. Well, if I want to relate that to the phase difference, which is basically going to help me think about whether my waves are adding up what's known as constructively or destructively, this is the expression that I'm going to use to do it. So you notice that basically the phase difference over 2 pi is equal to the path difference over lambda. And so what's important here is, again, phase is measured in radians. And so basically I'm saying 2 pi radians takes me all the way around the circle. So what I'm interested in is the phase difference is what fraction of all the way around the circle. That ratio is going to be the same as thinking about the path difference over the wavelength itself. So in this case, given that my wavelength is 1 meter, my path difference is 1 meter. So when I look at this ratio here, well, it's just 1 meter over 1 meter, which is 1. So the phase difference, to get that, I'm just going to say, okay, so I just need to multiply whatever this value is times 2 pi. In this case, that gives me 2 pi. And so thinking about special values of the phase difference, or special values of this ratio, the path difference to the wavelength, are going to tell me what type of interference I have. And in this case, basically what this says is my waves have perfectly lined up again, and the name we give to it when waves perfectly lined up is called constructive interference. So constructive interference, again, is the special case where our waves line up. And so you notice, or if we think about what's going to go on in this equation here, well, they line up when basically I've gone all the way back around a circle one complete time in terms of the phase difference. So if the phase difference is 0, right, that basically again means that my waves are perfectly aligned, they're in phase, I have constructive interference. If I go once around the circle, then they're lined up again. If I go twice around a circle, then they're lined up again. 3 times around a circle, then they're lined up again. In terms of thinking about the path difference, what that means is if your wave travels, if they travel the same distance, right, so your path difference is 0, they started in phase, they'll be in phase. If they started in phase and one of them travels exactly 1 full wavelength more than the other, then again they'll be in phase again. Or if it travels 2 full wavelengths or 3 full wavelengths, So again, as long as one of my waves travel, as long as the wave from one source travels an integer value of wavelengths longer than the other, then they're lined back up again, they're in phase, and I have constructive interference. So here you can see what that means is this ratio is just going to be integer numbers. And so when we think about what that means for values of the phase difference, that says values of the phase difference when it's 0 or 2 pi or 4 pi or 6 pi. So again, 0 or once around the circle, twice around the circle, 3 times around the circle, etc. Or path differences that are, again, 0, they travel the same distance, or one of them travels 1 wavelength longer, or one of them travels 2 wavelengths longer, or 3 wavelengths, or 4 wavelengths. So these are path differences that will give me constructive interference. And again, when I have constructive interference, what that means is the amplitude of my resultant wave is twice the amplitude of my initial wave. So this is a situation where I have constructive interference. The other special case we talked about was destructive interference. And so destructive interference are where my waves are completely out of phase, and so they cancel out and leave me with nothing. So the first thing to notice for destructive interference is that all my amplitude of the resultant wave values are all 0. Because my two waves are perfectly canceling out if I've got destructive interference. So when does this occur? Well, basically, it'll occur in terms of phase differences when I go halfway around the circle, or 1.5 ways around the circle, or 2.5, or 3.5. Right? So that's what these values are, right? Pi just tells me I went halfway around the circle. 3 pi says I went all the way around the circle plus halfway around. 5 pi means I went all the way around the circle twice plus halfway around. So these are basically situations where the phase difference all are off by halfway around the circle. Some number of full times around plus halfway around the circle. In terms of the path difference, well, again, to get these things out of phase means that I need one wave to have traveled half a wavelength farther than the other. If it would have traveled a full wavelength, they'd line back up again. So I need it to travel half a wavelength so that they're perfectly out of phase. Or I can travel 1 full wavelength plus an additional half wavelength, or 2 full wavelengths plus an additional half wavelengths, or 3 full wavelengths plus an additional half wavelengths, etc. So again, this ratio is going to end up being 1/2, 3 halves, 5 halves, right? So basically, odd numbers on top, 2 on bottom. That's what I want this ratio to be. This is always going to give me destructive interference, and so my two waves will cancel out. So those are sort of the two special cases. Everything else falls in between. So everything else we can basically think of as intermediate interference. And intermediate interference is just a way of saying they don't add up perfectly, they're not perfectly in phase, they don't cancel out perfectly, they're not perfectly out of phase. You just have something between twice the amplitude and 0. And again, what you can see is the closer you are, when we think about the phase difference first. Right? Well, I know that a phase difference of 0, they're going to be perfectly aligned and my amplitude will be 2. I know that at a phase difference of 2 pi, they'll be perfectly aligned again and my amplitude will be 2. At a phase difference of 1/2, a phase difference of pi, I know that they'll perfectly cancel out. So what you see is, as my values move from close to 0 towards pi, my phase difference goes from basically 0 to pi, my amplitude decreases. Here's, somewhere between here and here, it's gone from 3/4 pi to 5/4 pi, which means it crossed over pi. And so now as I go from pi to 2 pi, the amplitude's increasing again. So effectively, The closer I get to pi, the more my waves are going to cancel out. The closer I get to 0 or 2 pi, the more my waves are going to add together in terms of their phase difference. We can say the same thing in terms of talking about their path difference. So I know that if the path difference is 0, then they perfectly line up. If the path difference is 1 wavelength, they perfectly line up. If the path difference is half a wavelength, they completely cancel out. So as I go from a path difference of 0 wavelengths to half a wavelength, the amplitude decreases. Once I cross over half a wavelength and head towards 1 full wavelength, well, again, they're starting to line back up and the amplitude increases. So thinking about what the phase difference and path difference is in terms of intermediate interference can basically tell me, are my waves mostly adding up or are they mostly canceling out, depending on whether I'm close to a phase difference or a path difference value that corresponds to constructive interference. If I'm close to one of those, they'll be mostly adding together. Or if I'm close to a phase difference or a path difference value that corresponds to destructive interference, then they'll mostly be canceling out. So before we start worrying about our physical optics in terms of thinking about light as a wave and how it behaves, first and foremost, we're going to deal with just thinking about two-source interference and how we add phases together to think about the resultant wave.